So welcome everyone to something slightly different from River Publishers this time. Today I have with me a number of different people. So I have Nicki Dennis from River Publishers and Andrea Vacca from the Editor-in-Chief of our International Journal of Fluid Power. And today we are announcing and discussing the best paper from 2021, which was awarded to the paper A Digital Displacement Hydrostatic Wind Turbine Transmission. We have two of the authors with us today, Win Rampen and Niall Caldwell, to chat about the paper and its digital displacement technology. So welcome everyone, especially to Win and Niall. Thank you for joining me today. So perhaps just to start with, Andrea and Nicki, would you like to introduce the journal a little and kind of what it covers?
Yeah, okay, I'll go first. I'm the least technical person here, but I'm the journal's publisher at River Publishers, and the International Journal of Fluid Power is one of our little gems. It's been around for about 20 years, and it genuinely is the only journal that its total focus is just fluid power, which is hydraulics and pneumatics, and some of the maths behind it and the applications. And we have a very strong editor, which is why it's doing so well. And that's Professor Vacca, Andrea, who is based in Purdue, I believe. Pretty snowy at the moment there, Andrea?
Yeah, that is correct. I'm a professor at Purdue University in the United States, and I also lead the MHA Fluid Power Research Center, that is one of the best fluid power labs in the world, at least in the academic world. And yes, the journal, as you said, has a long tradition. It's a journal that was established by the Fluid Power Net International community. And then this community recently merged another community in Europe, and now we call it the Global Fluid Power Society. So essentially all the academic centers in the world, almost all of them, they are part of the Global Fluid Power Society. So with that, the journal that is the reference for the society has really a strong editorial board, and we always find very strong reviewers. And I believe that it's very hard to get sometimes a paper published in our journal because of the high expertise that the people have. So yeah, we have, as you said, a lot of submissions, many that they don't go through. So we have a quite selective process, but I think we are happy with the quality of papers that we have.
So talking about the papers and moving on to the winning paper, A Digital Displacement Hydrostatic Wind Turbine Transmission. Firstly, Win and Niall, congratulations on having your paper chosen out of the ones we had. I guess to begin with and kick things off, kind of what is digital displacement technology? When or how did you kind of come up with this idea?
Well, we came up with it a very, very long time ago, and it was to do with renewable energy really from the start. We worked out that if you're trying to harness natural forces, you tend to have something that's slow, irregular, high force, and you have to control that motion and transform it into something that probably is a shaft going round at a constant speed. And for that, you need a transmission, and the transmission has to be both intelligent, efficient, and controllable, and scalable. And so for that, at the University of Edinburgh, where I started out, we worked out that hydraulics were the right way to go, but we found that conventional hydraulics were not, they didn't tick all the boxes. They weren't quite big enough for what we had in mind.
Okay.
They weren't at that stage controllable enough because there was very little electronic control. I'm talking 40 years ago. And the real problem is that with renewables, you size, and for many applications, you size the transmission power that the system will experience in its lifetime. But in fact, in many applications, you're almost always working at a relatively small fraction of that.
Sure.
And hydraulics can be pretty good at high power once you've selected your components. But they tend to be rather poor in terms of efficiency at a low power rating once you've built your system. So we developed digital hydraulics as a way of creating a hydraulic transmission that would be very efficient even at very modest power throughputs, which is very important for things like renewables, like wind turbine transmissions.
Yeah, actually, I've got just an illustration, a slide here of the sort of very early work at the University of Edinburgh in the 80s, and this is Stephen Salter and his compatriot. And David Jefferies. I think Win comes in this slide a bit later on. But basically, they were working at this small scale, looking at, but thinking big, thinking about megawatt scale wind energy. And they came up with this duct device and studied it in great detail and realized that, yeah, they needed a very high power density transmission that could deal with very high torques that you get with obviously huge forces in sea waves. But it also needed to be controllable. So when they did the experiments, they realized they could get much more energy out if they could completely control when and how much energy was being absorbed. And so they needed this combination of very high efficiency at part load, as Win's explained, but also it being very controllable and being interfaced to a computer. So, and that's the concepts really went much further ahead than the technology available at the time to really implement them. And it was, this looking at the best available, let's say, conventional hydraulic technology at the time, just didn't look like it was ever going to reach the levels of efficiency and controllability that were required. And that's how I put it. That was the sort of the stimulating for this invention. Yeah. So. Yeah. Okay.
So looking at kind of wind turbines specifically, because that's what the papers focus on, how is this kind of used specifically in that case?
Well, most wind turbines are either direct drive or they have a fixed ratio gearbox, and they try and match the varying speed of the wind to the 50 or 60 hertz of the electrical grid. Neil's helping us out here, with a very big box of power electronics, which has traditionally been a bit of a power failure source. Both the gearbox and the power conversion have been both serious problems in terms of reliability over time, and the problem was getting worse as turbines were being scaled up. And the other thing was that a lot of the generators that were being used were what are called induction generators, and these essentially lean on the heartbeat of the grid in order to work. So if you put too many wind turbines up in a particular area, they can actually destabilize the frequency of the grid. So we developed a transmission which in principle solved all those problems and allowed us to drive something called a synchronous generator. And synchronous generators basically create the heartbeat of the grid. So they don't have that same shortcoming that other wind turbines up till then had. But the world moves on. I mean, Artemis was basically bought by Mitsubishi at the time, who were building one of the world's largest wind turbines. As a prototype, the world's largest floating wind turbine was deployed off Fukushima with our transmission. And in the lead up to the actual full scale, we built something about a 6th scale or a 5th scale in our own lab. And that hadn't been properly documented. And I have got 2 roles. I still have a role at now Danfoss, but previously Artemis. But I'm also at the University of Edinburgh. And I thought, with my university hat on, it was time to actually record what we'd achieved. And although I'm doing some of the talking right now, it really has to be pointed out that we wouldn't have achieved very much at all if Neil hadn't actually made a superhuman effort in terms of getting the actual thing to work in Japan. At one point, he was sort of leading a troop of about 100 Japanese engineers getting these large-scale machines working, which ultimately they did. Anyway, come in here.
Fantastic.
Yeah.
Yeah, I mean, I've got a few more just pretty pictures. Actually, about the history.
I was going to say, let's see it.
Wind turbines, have actually been made with hydrostatic transmissions before, and there was actually an effort in the late 70s to make. It was at the time Europe's largest aerogenerator.
Wow.
But the problem was really the efficiency. They couldn't get the efficiency, the controllability, the scalability, and so we really needed to unlock that with this new technology. So really, to be in any way competitive, we needed to be in with the big scale of multiple megawatts. So not just 30 kilowatts as in this case, but actually megawatts and above. So that was a huge challenge, actually, based where we were at the time, with maybe a few hundred kilowatts to make that leap to that scale. But there was sort of behind the scenes a vision that was there from Stephen Salter from the early 80s about just how scalable digital displacement could be. And he was thinking 30 megawatts at the time. And one of our greatest disappointments is we didn't quite manage to reach 30 megawatts. But basically,
still alive.
There's still time. There's still time. So there was this sort of vision out there that when the technology could be developed, then it would, in theory, be capable of being applicable to very large wind turbines. But it was unproven. So we sort of conceived of this, and this is for a long time was Win's, his own sort of project in the company. There was many other things going on in Artemis. This is the background of this. Is at the time as this was Artemis Intelligent Power, developing digital displacement technology for many different applications, and Win was very much leading the charge on saying that wind is going to be the big thing. And the basic idea is you have a digital displacement pump connected to the turbine. And you have a digital displacement motor which drives the generator. But the sort of key difference here with what was done before was that this digital displacement pump was to be direct driven from the turbine, so it turned very slowly, but it was also to be variable displacement, so to have full controllability, the ability to store energy, and the ability to very rapidly respond to changing wind conditions and emergency conditions. We needed to be able to control that pump. And that actually was a device which didn't exist. We're talking about a variable displacement ring cam pump, which really, actually, for those in the industry, was thought to be, well, that can't exist because there isn't a mechanism that can make that vary its displacement. So that's really what uniquely digital displacement could do is enable for the first time a variable displacement ring cam pump, and also do it at very high efficiency with very high control. So we could make this hydrostatic transmission, and they sort of conceived of it, fitting, inside a nacelle like this, but developed proof of concept hardware to prove that it could actually work. And it's really this hardware that is written up into the paper, and it's the analysis of this hardware and the early test results. And it was those test results that gave confidence to Mitsubishi to invest to scaling it up yet further. So you can see, two of the machines that were developed, the ring cam pump in the bottom left, and then the 800 kilowatt pump, high-speed pump motor in the top right, and those two devices were really the core of the development in the early stages.
And that's effectively we started writing a paper, and we were going to do analysis of both of these machines as well as the overall transmission. And what happened was it got very large and unmanageable. So we've actually decided to publish it as 4 parts. So you've had the first part, which is actually the final thing of what happened when we put it all together. But the second part, which is dealing with the analysis of loss in the pump, is it's 95% complete. There's 1 or 2 funny data points that we're trying to figure out how to resolve, which just create a bit of inconsistency in the data. But basically, the paper is written, and we hope to submit it before long.
Oh, great. Happy publisher.
Okay.
Okay.
I am curious. So, when you were doing this with Mitsubishi, there were some rumors, and I was so curious, as so many of our colleagues, but of course there was not much that you could share. After a few years, can you share more? Is this a technology that they will, after this big prototype that you put in place, do you think there is a chance that they will pick up, and we will see turbines using that sometime soon. What do you think?
There's been a lot of churn at Mitsubishi, and all the time that we worked directly with them, they kept moving the goalposts. So I'm being careful what I'm saying here. So they decided that commercially forming joint ventures was a good plan, and they did one with Vestas, roughly at the same time that they bought Artemis. And so there were actually 2 tracks to produce a turbine of about 7 megawatts. And the Vestas prototype was well ahead of us in terms of technical development. There were actually pre-existing 7 megawatt prototypes on test when our transmission was really still in its infancy. So ultimately, I think in that joint venture, the 2 different tracks were seen as kind of competing with one another, and ours didn't really progress that far before they committed. MVOW, or Mitsubishi Vestas Offshore Wind, committed to the Vestas machine, which is being sold in numbers now for offshore wind. And incidentally, Mitsubishi very recently sold their part of the joint venture back to Vestas. So it has changed a great deal. Mitsubishi has retained their interest in our hydraulics, but it's not obvious how that's going to materialize into a larger machine at this point, which of course we would love to see, but we got left. Mitsubishi has now sold Artemis to Danfoss. And so we're really focusing. Danfoss is very interested in a different area, and Neil is far more involved with that in a direct way than I am. So I think Neil should maybe talk about that.
Yeah, I mean, it is. I think as inventors, as technology, let's say, proponents, you have to think, well, there's only so much that we can do. You can lead a horse to water, you can't make it drink. And what we had to do was to develop the technology, show that it's feasible, make it work, make it efficient, make it reliable, and so on. But then at the corporate level, there were things that were going on that we weren't even aware of. Mitsubishi had a number of horses in the race, and one of those horses actually was further forward than we were in terms of overall maturity. We're not just talking about the transmission, but the whole turbine. So the Mitsubishi development that included our turbine had new blades, it had a new hub, it had a new tower. The whole thing was new, and the whole thing was Mitsubishi. And ultimately, when they looked at the relative maturity of the Vestas machine, they realized, actually, do you know what? We're years behind from all different angles. And they decided to put their money into the Vestas. So we still came out of that feeling, well, we did something groundbreaking. We did generate actually 2,000 hours of wind energy into the Scottish grid, with a 7 megawatt turbine that was stationed at Hutcheson. And that gave us a huge amount of pride when we used to go into the office in the morning, and we would see a little monitor on the wall with data coming from our turbine, our little pet turbine, that was, had 160 meter blade diameter and was sitting on the west coast of Scotland, generating, sometimes you'd come in and, 7 megawatts. That's great. Oh, switch the kettle on. Great. We're putting 7 megawatts into the Scottish grid. So we did, that from that point of view, we feel we made the point for hydraulics as well. And that's another thing, is that for team hydraulics, I think it was an important that we put that marker down. We can be just as efficient, just as controllable, and we can aspire to those heights as a technology. And I think that's something that is really important for hydraulics. It has a future. It has a really bright future as a technology, and that it's not just going to be stuck in one sort of design. It's actually going to continue to evolve, and there'll be future designs, and I think that was another thing that we feel came out of this project, was just that we almost broke the limits of what hydraulics could be thought to do, And so that's something that we're proud about as well.
I guess the other thing that is not obvious, and probably won't even be obvious when we complete this suite of papers for these smaller machines, is that the large ones were in fact the largest, most high-power hydraulic machines ever made. And when we built the prototypes for what went into the turbine, they were very early attempts, and during the time the turbine, after the design was frozen, the turbine was built, we carried on developing components actually at Artemis, and we actually were in a position to build a much better motor and pump at the end of that process, those components never actually made it into the actual turbine. So we learned an awful lot during the sort of 6-year program that we were involved with, but it was a bit disappointing in the sense that you know, it was so groundbreaking because of the scale that it took a long time to get some of the components up to the level of capability, performance, durability that we were looking for, and they didn't actually make it into the final machine. Yeah.
I do actually have this might be of interest, but I've got some video of the what we were doing when we were making the data for this video. So in actual fact, where this came from was a test rig that we built in Edinburgh, and this was basically, we had these machines, we just told you about these new machines, and we had to build that into a demonstration system in the lab. And this is the digital part of digital displacement, all the flashing lights. You've got to have flashing lights. But each one of these lights flashing relates to one of the valves in the machine that's controlled by a solenoid. And then so that was the complete system, but we also developed some subsystems, so the generator drive. So this was synchronization to the grid. And this was something that was actually quite difficult to do from a control point of view, because we had to very accurately control the power output of the hydraulic motor and bring these two waveforms into synchronization, and do that within about 10 seconds from startup. So that was, there were a number of sort of building block technology demonstrations we had to do to give Mitsubishi confidence that the transmission could actually do all the sequences of operation from startup, normal power, and shutdown. And that was another output of this test rig. So we generated all this good quality data for efficiency that is in the paper, but it also generated a lot of other case studies and simulated operation for the just for the complete operational needs of the turbine. But the other, I think Mitsubishi just had an incredible resource and drive to take this onwards. And so, having done the proof of concept, we then teamed up with a team in Japan, and a lot of faces that we worked with very intensively, and very big groups. And the amazing achievement of Mitsubishi is just not to be underestimated. To go from this was the first demonstrator at 2.4 megawatts in Japan. And you can see that the scale of the whole thing is huge, and the amount of data that was being generated, and also the human resource needed, just the commitment of people and facilities to take this to demonstration. And then together we scaled the technology up to 7 megawatt, and then they built this machine. And this machine, I remember the day I turned up and saw this, and I just couldn't believe my eyes. It's the size of a house. And it's not made of bricks. It's actually precision engineered machinery, and the scale of it was extraordinary. And this is a hydraulic motor. I mean, hydraulic motors don't usually look like this, but it looks more like a diesel engine. But this is a 3.5 megawatt hydraulic motor, and so all of this work was being done by Mitsubishi, if you like. For Artemis and for us, this was just beyond our ken. The scale of it, the number of people involved, just the huge, scale of all these different components, and ultimately, this test rig, it shook the ground. I mean, and if you got it wrong, if you put the wrong number in a box, then you felt it in a sort of earthquake through the ground. So it was a pretty awe-inspiring machine that ultimately came out of it, but also I would say an awe-inspiring sort of scale of development. It was the other thing, and then once that machine was sort of, once we made the transmission and put it together with all of the other elements, the blades that Mitsubishi designed, the tower, all of the balance of that system, then this is what got built in Scotland at Hutcheson, in this amazing sort of valley of construction that was wow. Also awe-inspiring to see. So yeah, it was a pretty incredible engineering display, I would say, that Mitsubishi put on, and ultimately, as I say, did generate energy into the Scottish grid and indeed into the Japanese grid. So it for a while was the world's largest floating offshore wind turbine in the Sea of Japan off Fukushima. But of course they had the terrible nuclear disaster, and they wanted a new way forward, and it was offshore wind and floating offshore wind, which is required in Japan because of their deep seas. And so this became, for a few years, it was the world's largest floating wind turbine, and all controlled from an office in Tokyo by Noguchi-san there. So yeah, it was that's a little bit more sort of background and colour to the development.
So is it still out there now? Is it still out on the system?
It's not. No, it's not. It's not out there anymore. In fact, it wasn't even the transmission things that were the limiting factor. This was a 5,000-ton floater with welds, just the maintenance of that and the stresses and the strains of that in the sea waves. It was incredibly cutting edge technology on lots of different lots of different fronts. So it was so it's not out there anymore, but it did do its job in terms of proof of concept.
Definitely.
So, yeah, very exciting. Yeah.
So, but you did ask about what we're working on now. What's going to happen? I think I didn't quite get to that, but we're actually working now on a smaller scale. We're not really working at the 7 megawatt scale, but we are working at the hundreds of kilowatts appropriate for the big off-road equipment like excavators and wheel loaders. And these are machines which today use a lot of energy, create a lot of CO2, diesel engines. So if we think construction machines overall, about 400 megatons of CO2, and that's about 10 times the whole of Scotland. Construction machines worldwide, and about half of that is excavators. But the problem with excavators is the systems are not very efficient. In fact, 70% of all the energy from the engine in an excavator is turned into heat in the hydraulic system. So that's the big opportunity that we've decided to tackle. Is where we can make the most impact with our technology is by transforming the efficiency of hydraulic systems in off-highway machines, where they've got industries desperate for solutions. It's not easy to electrify an excavator, especially the actuators. Elon Musk is not going to solve that problem for the industry. You've got very high forces, linear actuators, multiple movements at once, all having to be controlled, and a machine which works in very harsh environments remotely from power points. So it's very difficult to transition from diesel engines. But actually, the low-hanging fruit for the industry is to improve the efficiency. Certainly, in the next to 2030, there's huge strides that can be made to reduce the CO2 emissions of machines like excavators simply by reducing waste. And that's what we've been working on. Really, our focus since the acquisition by Danfoss, and well before that, actually, really since the wind project sort of wrapped up, we shifted focus completely onto mainstream hydraulic applications. Rather than trying to create a whole new market for hydraulics, which we tried to do, we thought, well, let's just engage with the existing hydraulic markets as they are and see if we can use our technology to solve those problems. And that, so we've made some demonstrations in excavators. In fact, 30% energy saving in a paper just last year, I think. And we're continuing to work on that R&D in the lab in Edinburgh. We're continuing to develop, and now we're working on energy recovery, which will take us, we think, from 30% to 50% savings. So we're seeing the sort of results we're seeing in the lab now give us some confidence that within 10 years we should be able to make excavators that really use half the fuel of today's excavators, while still doing just as much or even more work, because less waste means more productivity. So I think there's a rising awareness now in the industry of efficiency as a hot topic. And digital displacement is just one way of doing that. There's many other innovations going on, looking at efficiency, many different architectures. Previously, I've been told by people in the industry that efficiency just didn't really sell, because basically fuel was too cheap, and many of the end users just didn't really care too much. But that's really changing. In the UK, this year, the UK fuel for excavators will almost double in price. The government has taken away a tax rebate, but also the big manufacturers are making commitments, science-based targets to cut their downstream CO2, and so there's a big focus now on efficiency, and so we, at the right time, and with Danfoss there for the market access, manufacturing, and so on, with their investment, effectively we're now tackling this, and so I think that's probably, in terms of direct impact to the climate and the big challenges, that's probably going to be the biggest impact of the development. That's what we see it as we see it now.
Thank you so much. I'm afraid I'm going to have to start bringing it to a close because we're running out of time. But Andrea, would you like to just finish by explaining a little bit about why you chose this particular paper as the best paper from Fluid Power in 21?
Well, first I have to say that I was really enthusiastic when more than 1 year ago Win called me and said, well, what do you think? I have a paper that is behind the effort that we did, and of course we talk about, they explain very well what they did. Do you think it's suitable? And he was so humble and said, the world was, the fluid power world was really observing what you were doing there. Was so breakthrough, and I was like, please send the paper. And I remember after a few weeks calling him, do you have the paper? I was afraid that he was going to send somewhere else. And so eventually the paper came in, and that was expected is the paper that by large had the most views. We ran statistics on downloads and views of the paper, and so that was a clear parameter. But of course, we want also to give the prize to the papers that are technically sound, and so the board of directors, so those are all accomplished professors, view the paper, and we selected the top three papers out of those parameters that I mentioned before, and all of them, they agree that this should be the paper. So that's how we came up with that decision. Yeah. And congratulations.
Yes. Congratulations, Win. Thank you everyone so much for joining me today. It's been really interesting. And yes, congratulations again.
Congratulations both of you.